So it's lecture number 2, T211 analog circuit design. Yep. So last lecture we talked about some introduction and we talked about transistor like MOSFET. So why we call it MOSFET, by the way? What is the reason of MOS? Because of its structure where it's metal oxide and semiconductor, and it is field effect transistor, means it's voltage operated. So it's voltage operated. Other side we have BJT, which is current operated. Uh, there is no need to come next time if you are coming after now, please. Okay, there is no attendance receipt. Okay, there is no need to come tomorrow if it is more than 9. Okay. Can you lock that? Can you lock that? Yeah. So this is current operated and this is voltage operated. Yeah. So this is voltage operated. This is current operated device. You must have studied basics of MOSFET and BJT in IC 161, where for the case of BJT, you know the current equations, right? What is IB, by the way? What is IB? So different versions are there. Yeah. So different versions of different equations are there. However, like people like to write only this one, right? You can write down -1 also. Okay. But do you know the equation for MOSFET? Because as per my knowledge, you have studied MOSFET a little bit, right? So do you know the equation for current equation for MOSFET? Okay. Before moving to that, in BJT, what are the various region of operation? Do you know that? Yeah. What are the different region of operations? Active mode, saturation, cutoff. Yeah. So you know about all this, right? You know the characteristic also, right? Note that active mode of the operation is the one where you can amplify the signal, right? Your transistor has to be in, if it is BJT, it has to be in active mode of operation. If it is in saturation mode of operation, it will not amplify, but it can be used as a switch because the relationship is linear. Right? So this is right. So you must have studied this one. This is saturation, and this is active. In active mode of operation only, the equation of IC and IB are valid. Otherwise, they are not valid. By the way. Yeah. So these equations are valid only in active mode of operation, and here only you can have the amplification. Otherwise, there is no amplification. If you are in saturation mode of operation, you can have only and only transistor as a switch. Okay. So this was just referring BJT. In case of MOSFET, by the way, this equation is for N channel, by the way, N type BJT. This is NMOS FET, where the characteristic is similar to what you have studied in BJT, but this is VDS with respect to ID, where ID is drain current and VDS is drain to source voltage. And note that the curve which is uh, making two different region of operation, that curve is not straight, it's exponential one. This line is known as VGS minus VTH line, or it's also known as VDS when it's in saturation. So VDS set line, you can call it. It's red color. This side of the VGS minus VTH line, it's known as saturation. Generally, people make such mistake when it's asked that draw the characteristic of BJT and MOSFET. They are drawing the correct one. They make mistake here, VGS minus VTH line, and they are making mistake in the mode of operation. Here you can see that saturation mode of operation is other side, whereas in in MOSFET it's this side, and other side you have linear mode of operation. But there is one more name called triode. So any of the name is there, and other than that, that one, it's called cutoff region. So in saturation, the current equation is mu n Cox by 2 W by L VGS minus VTH square. This is the equation. We are not going into the detail how it has been derived. It's a physics, so it will take at least 7-8 lectures if I start teaching this one. So it's not part of this course. Right? So just if you want to know the detail of this one, if it is not covered in IC 161, but there is one more course called CE 311 or 301. 311. So device electronics for integrated circuits. This will cover this equation. Actually, the half of the semester you are going to study only this equation, the derivation of this using Poisson's equations, right? And Schrodinger. So then you are deriving the charge sheet model, and through that you can derive this. So it's a separate thing, but it's a device physics. But if it is in linear mode, the drain current is mu on Cox W by L. So for the linear, this is the equation. So this side different equation, and this side it's different equation. Okay. You just keep it in your notebook. The derivation of this one will coming in other course, right? But if you don't know the derivation of this equation, still you can survive in analog very well. No problem. It's not required. Okay. So by the way, mu n is what? Mobility of this n type semiconductor, right? So NMOS, that's why it's mu n. Cox is oxide capacitance. So the if you look at the structure, which I have shown in isometric view. So this is gate, this side is drain, and other side is source, and this is P, and it's bulk or substrate or body. Generally this goes to ground, right? So there are 4 terminals, but if you look at the top view of this one or the elevated view looks like this one. So generally most of the books you will not find the isometric view, but it's only the elevated view, which looks like this one. So this is gate, this is source, and other side is drain. But unlike the BJT, you can exchange drain and source. So whichever you like, you can keep it drain or source, and that's how like the symbol of this one is like this. You are not required to indicate that which side is source. The lower potential may go to source. Right? But this is what I told, the interchangeable characteristic. It's valid for only for few amplifier schemes. There is one scheme which is known as common drain amplifier. It's not valid, so we'll study that. But till that, assume that source potential will be lower than drain. And if you are looking at the top view will look like this one. But I'll explain this a little bit. This side is drain, this side is source, and this is gate, right? That is how it looks like. So if you look at this vertical side, the oxide capacitance, if you remember my previous course where we talked about the thing on parasitics. So parasitics, if it is talking about the capacitance only occur at high frequency, and if there are two dissimilar metals, then it creates a capacitance, which is parasitic capacitance. So here you can see, so here this is one capacitance which is Cox. You can see here N plus and P has one capacitance. This one has one capacitance. You can name them as like this is B, D, S, and G. So you can call this one as CGB, which is eventually known as Cox, oxide capacitance. This one is known as CDB. This is known as CSP. Right. So all these are dissimilar metals are creating capacitance. You must have heard about. Is there any doubt here? So if you have heard about something called technology node by a gentleman called Moore. Have you heard about him? Moore, founder of Intel. Okay, so you can read about him. So there is very famous Moore's law. Now you know about what is Moore's law. What it suggests. So it suggests that all these things are belongs to the IC technology or the integrated circuit technology. So every 1.5 years, the number of transistors which can accommodate in a given area, it will be doubled. Every 1.5 years, it has to double. And for this, the transistor size has to be decreased by 0.7 times. So there are some specific things are happening. And this is possible by Moore because Moore was running his own company. So he was saying that this is the law for my company and every other company has followed him blindly. That's why it becomes Moore's law. So 0.7 times it has to be decreased. So currently in design we are using 14 nanometer transistor. That is a minimum one. Not yet launched. Uh, any of the circuits are not being like product wise. They are not launched in 14 nanometer. However, 21 nanometer, 28 nanometer are the regular one where you can see all the circuits as designed. Means Samsung's phone or iPhone, all other mobile technologies are using 21 or 28 nanometer currently. That's how they are so much small. So 14 nanometer in maybe a few months, the next release of maybe new phones will have 14 nanometer, right? So this was about Moore's law, and when we are saying this 21 nanometer and 28 nanometer, it's all about. I'm removing the parasitics, and if you look at the length of this one or the size of this one, it's known as length, and if you look at here, this is known as width. So length and widths are defined here. This length is the one which we are talking about in terms of this transistor size. When we are saying 21 nanometer, means this length, the minimum length is 21 nanometer or 28 nanometer or 14 nanometer. You cannot go beyond below that one. That is the meaning of this one. Okay. So now let's, okay, we can complete this one also. Like we can see resistances also. They are available at any of the frequency, and it needs to have the path. So if I am drawing a line from here to here, so 1 and 2 are different nodes of circuit. If they are connected by wire, the path will have resistance. That's known as the parasitic. And if you are dealing with 1 and 2 in high frequency, it's not only have resistance, but it will also have capacitance. Similarly, if you are at very low frequency, it creates inductor, and you have to create a circle or the closed path. Then it creates inductor. You can create turns. Through that, you can have inductor. Right? So this is the parasitics. This is going to be very useful for understanding the frequency response of BJT or MOSFET. Okay, let's move back to the place where we were. So NMOS, if you are using as a switch, there is something called turning on voltage. Right now, when I'm saying NMOS as a switch, it has to be in the linear mode of operation, because linear mode of operation has the linear relation. Different value of VGS will give you different curve, right? Something like this. So if you are in linear mode, this will act as a switch. If you are in linear mode, the equation governed by this switch is equal to mu on Cox W by L, VGS minus VTH, VDS minus half VDS square. Note that here W and L are the width and length of the transistor, which I have shown just now. Right. So we are referring to this width and length. And VDS is drain to source voltage, Cox is upstream capacitance, and mu n is mobility. Right? So this is the symbol. If the author has not kept body potential, if it is not given, note that if this one is not drawn, body is not there, then you have to assume that in the case of NMOS, it's connected to ground, and in the case of PMOS, it's connected to VT. So all the authors are following this terminology. So right now, it's not connected anywhere, means it's connected to ground or it's connected to VT. Unfortunately, it's not explicitly mentioned in any of the book, but assume this one. Okay, so if that is the case, what this switch does, it acts like a valve, where this side is source, this is gate, and this is drain. So if gate voltage is high enough, or you can say that it's higher than this line, which is VDS set line, or the potential at which the transistor go to saturation mode or to go to linear mode, that govern this entire device. So if that is sufficient enough to keep it in linear mode, you can have Vs equal to Vd, right? If gate is enough, just to make sure that it's in linear mode, right? So if I am drawing the equivalent model of such transistor as a switch, what I am expecting as a switch, I want that if it is on, it's short circuit. But this is not possible. You are going to connect it with some path, so there has to be some resistance, and I'm expecting this resistance to be 0, right? And similarly, if you are operating this one at high frequency, all the parasitics will be on. There is one more important thing which I forgot to tell you. So all these transistors and everything is being made by not by human. It's by robots or some technique or some different machines are there. While making this, you need certain environment where for a cubic area only a few diluted molecules are allowed. So we have various environment. One of them is known as 10, 100 or 1000. This is equivalent to the how many diluted molecules are there inside that particular environment, and we call this one as class 10, class 100, class 1000, and maybe class 10,000 also. But so fortunately, like in India, only 3 places are there where the class 10 is there. One of them is IIT Mandi. So if you go to C4D FED center in South Campus, we have class 10, class 100, class 1000 facility. Through that you can make the transistors. If you are interested in this course, there is one elective course called VLSI technology that you can take. And if you are interested to make the transistor, it's called VLSI fabrication practical. These are generally happening in even semester only, right? So if you wish to go into this particular area, you can take that one. So when we are talking about these transistors in different classes, this is the elevated view. I want to make this transistor, but this is in submicron or nanometer scale. I wanted to make this one as 14 nanometer, but it's very difficult to make 14 nanometer. It will be something plus or minus delta. I call it delta L. And similarly, I wanted to have exactly same age of this one, but it's not possible. There will be some overlap. You see, I wanted to make it here, but it has shifted outside. It's very difficult to make it exactly aligning this particular line. So it's not possible. So this is the real model of the transistor, and here you can see that gate to source and gate to drain. There is another overlap area which is going to create a capacitance whose names are CGS and CGD. However, these are known as overlap capacitances. Right? So here I am just drawing this. If you are working at high frequency, CGS, CGD, CSD, but CSP, CDB, all these things will be there, right? So that is what going to happen. Effectively, there is a big capacitance, combining all the capacitance and keeping here. So this will limit the. So let's assume that this is very popular thing which you have studied in BTech first year IC 160 course, the RC circuit, right? So if I am applying here 1 megahertz of frequency, let's say sine wave with 1 megahertz, and this value is 1 kilo and C is equal to 1 farad. What do you think? What will be the output? Or let's keep it what do you think? What will be the output? Yeah, Gaurav? Yeah, both Gaurav. Third year and second year. So what do you think? Any guess? Anything? Ankit? Any guess? It's not a surprise to you. Yeah. So what do you think? What should be the output? Yeah, Dipti. Any guess? If this is 1 volt, like 2 volt peak to peak sine wave with 1 megahertz output, as this is a switch, I am expecting to have the same thing at the output, but am I going to get the same thing or not? Capacitor? So what will be the output? Okay, I am saying it's 0. Let's define this one. Now it's easy, right? Why 0? Why short circuit? It's short circuit, so same thing is here. If you don't like this one, let's make this one as one square wave, right? You have studied this one. For a square wave, what is the output? If you remember, the square wave of 1 megahertz, this is 1 microsecond, this is 0.5 microsecond. If it is passing through R and C, whose values are 1 kilo and 1 milli, the time constant of this one is 1 second, right? So to go from 0 value to this value, it requires 1 second. Means I am starting from here. Let's assume that this is 1 second. So after 1 second, it will reach here, right? Something like this. If I am not applying the square wave. But after this point, it changes the state. So after 1 second, it reaches 0. Something like this. After some time, like it has to reach. So it will be, for sometimes it's like this, but afterwards it becomes 0. It dies out. This is happening because this does not have enough bandwidth. Or let's look at it in a different way. This is an RC filter whose bandwidth is 1 hertz. Right? It's 3 dB bandwidth. It's 1 hertz. So if you are applying anything like 1 megahertz, what will be the output? You can see here and you can say magnitude with respect to frequency. What does it suggest? That if you are at 1 mega, the magnitude VO with respect to VA will be much lower than what you are expecting, right? Or it will be attenuated by minus 20 dB per decade. Yeah, you agree with this one? So all these things are depending on the transistor equivalent model none of the circuit will be there which does not have any parasitics. All will have parasitics, and all will create R and C, or all will have the some bandwidth. So this is the limiting factor for us. R, C, sometimes L also, right? But if you are at very high frequency, gigahertz, terahertz, or even kilohertz, all are high enough so that it will limit your speed. If you are applying some frequency at source side, which is much higher than the speed of the transistor, then it will not work, right? So that is the problem. And the bandwidth of this transistor is known as Ft of the device, or the transit frequency of the device. So before to start, we have to know what is the transit frequency of the transistor. In general case, if you are, because I remember following things, 130 nanometer I remember, and 28 nanometer I remember. So 130 nanometer has around 300 gigahertz of Ft, and this one is around 500 gigahertz of Ft. So if you want to operate your transistor beyond that frequency, it's not possible. That's the main limiting factor of all the analog circuits, that cannot be going beyond 5G, right? People are designing 5G. So this is one transistor. If you are connecting many transistors, there are many R and C like this one. So many R and C will be there in cascade or in cascode, and creates a problem. So that frequency will be much lower than this 300 or 500 gigahertz. Or you can run your transistor maybe around 3-4 gigahertz effectively. So that's how like all the things are limited. So any doubt to understand NMOS as a switch? So we expect this, and if this is not on, but if it is off, we are expecting that it has to be open circuit, right? We want this open circuit, but because of overlap capacitance, there is a path from source to drain. There is a path. This is known as leakage current. So this is in off state, right? So any problem in understanding this one? Okay. So this is revisiting the MOS transistor layout taken from Behzad Razali book. So I follow only Behzad Razali, either blue color or red color. Right. Both the books have same diagram is available. Right. So here you can see that there is some overlap area. Right. So you wanted to draw electron as some value 14 nanometer or 28 nanometer or 32 nanometer or any technology you wanted to make, but because of this overlap, it will be having some different L effective, and that's how like when you are going to simulate the transistors, you will see different characteristic, and if you are going to have the measurement in the laboratory, it will have different value of current, because in this current equation, one of the player is length. So this L is not L, but it's L effective in the case of saturation, if I am writing this equation in saturation, right? So this L has to be effective length, and similarly W has to be effective, but L effective is creating lots of problem because there is a path from source to drain which is created by this length. Okay, you remember this one, periodic table, just to start like reading this thing. So the column 3, column 4 and column 5. Why we call it column 3? This one is column 4 and this one is column 5. Outer orbit has the valence electrons, right? So this has 3, this has 4, this has 5. So we have picked up silicon to make this transistor. Similarly, you can make germanium also and carbon also and other things also, but they are not so much easily available in terms of fabrication. Fabrication is not so much comfortable. In the case of silicon, it's designed by all USA, right? There is Silicon Valley where they have make all the companies where the substrate is silicon always. Otherwise, if you are in actually in BJD, germanium is used. If you are designing something for space application, carbon is used. But the main thing is you have to use silicon because of USA has invested a lot of things in Silicon Valley. If you want to do something else, then like you can do it in India, something like Himachal Valley, right? So if you must have studied about lattice structure in chemistry or in physics, right? So where you are connecting all of them in specific structure like lattice structure, they are connected with a covalent bonds, right? So the main thing is how to create a current. Current will create when there is transfer of electron, or let's assume that this is a metal rod. If I am giving the fire from here, then effectively there are lots of electrons, but they are not in the moving condition. That's why you don't feel anything here. So when you are doing this, you are breaking one bond, one of the bond, and there is electron is liberated. So what happens when this is liberated and it will sit on some other place? So when there is an electron, it's electron, and when there is no electron, we are calling it hole, right? So when it's sitting on top of this any of the available place, it's known as electron hole pair, and when it's moving in the direction of that, you will have the current, right? Or in the reverse direction of hole, you will have the current, right? Any of the way you can take it. So this is because of the thermal energy. Somebody has given the thermal energy. You have to give something so that this will be the moving electron. So this is the thing how it moves, and you can call this one as creation of hole or availability of electron. So now next thing is phosphorus, which is coming from column number 5. This is known as phosphorus impurity. Coming from 5, it has one extra electron, right? Not only 4, but it has fifth electron. So now if this is available, if you are having so many phosphorus, not only this one, but you are adding so many phosphorus, adding this one is known as doping. If you are doing it very high doping, we are going to call it P plus. Adding P not only few, but you are adding more than required, sometimes P plus plus also. So it depends on the numbers. So it's all about doping, how you are doing it. So phosphorus is dopant over here. So if you want N type or P type semiconductor, you are going to make either with column number 5 or column number 3 with column number 4. Column number 4 has silicon. You can also use other things like carbon or other things like germanium, right? But in the case of that one, if you are adding the boron, which is in column number 3, it will create one hole, right? So this is P type semiconductor. Earlier was N type because here electrons were available, right? The same thing which you have studied in your school time, right? So intrinsic and extrinsic. Do you want me to repeat this one just to like completeness I am teaching this? You know, then we can skip this. Is it okay? Okay. So now let's go back to our circuits where we were using the two-port network for Y parameter. So in Y parameter, you must have remembered this kind of structure. So now I'm asking you, let's make this one, derive it, and give it to me as a surprise quiz number 1. Okay. Now this is quiz. So there are only five quizzes. If you are coming late, it's your problem. Okay. So you have to derive the two-port equivalent model for BJT. I'll help you. Don't worry. I'll help you. So, if you look at this carefully, in the case of BJT, if this is a BJT which looks like this one, this is collector, this is emitter, and base. So this is a current control device. You are giving current at the input or IB. This side IC. Right. Generally, this one is, let's say, ground. I know following equations. IC is equal to beta IB. IB is equal to I0 exponential VBE by beta VT, or maybe just VT minus 1. And you have to replace this with two-port network, which will look like this one. This one. So this will become IB, this will become IC, this will become VBE, this will become VCE, right? And now Y11 is equal to del IB by del VBE, Y12 is equal to del IB by del VCE, and Y21 is equal to del IC by del VBE, and Y22 is equal to del IC by del VCE. You have to just derive this and you have to plug those results here. That will make the two-port network equivalent network for BJT. If you need my help, I can help you. No problem. I can come to your desk and I can help you. Rahul, Vivek, can you help others if they need? Just check whether they are going in right direction or not. By the way, in the equations of IB and IC, there is no VCE. You see, there is no VCE. So in that case, Y12 and Y22 goes to 0. Right? Because derivative of collector current with respect to VCE and base current with respect to VCE will go to 0. Right? So Y12 and Y22 has to be 0. Yeah, you agree or not? Just you have to find out Y11 and Y21. You have to take the derivative, partial derivative, and you will have the answer. It's very easy. You can start from here, where IB is equal to I0 exponential VB by VT. If you do the derivative, what are you going to see? It's a simple derivative. You have done much difficult than what we are doing now. Manvendra is here? No. Find out Y11 and Y21. Find out y1, y2. Find out y1 and y2. There is no need to draw this. Just find out 4 parameters. Find out 4 parameters. Only 4 parameters. Maybe at the end, the circuit will not look like this. Because y1, y21, this is 0, and this is also 0. So your circuit will only have 2 branches. If you take minus 1 also, it equals to 0. Derivative of that one is 0. It doesn't matter whether you take minus 1 or not. It's same answer. Right? Okay, for those people who forgot the equation of IB, please do not forget the equation of IB or ID. Now it's okay. Those who forgot the ID equation, this is same equation which is used for diode also. Right? Diode equation also. So who got the answer? All. This guy got the answer. Yeah, got the answer. So what is y1? I hope I have not made any mistake. Yeah. So minus 1 equals to 0. Are you getting same answer or something else? Are you getting same answer? IC by beta Vt. Maybe like if you are adding eta, in this equation eta has been taken as 1. Right? If you are considering eta, then it's beta times eta Vt. So as we already know that y12 and y22 are 0 because of non-availability of Vc in the equation. Whereas for y11 and y21 you have some answer. Let's call this answer as like IC is equal to IC by beta Vt. Let's define that one as 1 by R pi. This is for just easy usage. We are going to call this one as 1 by R pi. Because the units of this one is mho, right? So that's why it's 1 by R pi. Similarly, y21 is IC by Vt, which becomes or which is known as Gm or the transconductance. So if you got this one, then the final answer will look like this one. The final answer will look like this one, right? Where this one is y11, this one is y21. Y12 and y22 are 0 because the derivative with respect to Vc is 0. Is it okay? So This is known as transconductance. And remember this circuit, we are going to use this circuit forever. Those who want to stay in analog circuit design, they have to remember that BJT's model looks like this one. Equivalent model looks like this one. Now, you have to tell me following things. And you have to write down in your surprise list what is the impedance looking into base, impedance looking into emitter, impedance looking into collector. Whenever you want to find out the impedance, you have to follow only one gentleman, Thevenin, right? So when you are doing this, you have to make sure that all other terminals are zero, right? If you want to find out the impedance at particular terminal, you have to apply the node voltage VTH, and other terminals or the other input terminals will go to zero, and you have to find out the current flowing into the network. That current divided by voltage is known as the equivalent Thevenin or equivalent impedance. So find out what is ZB. What is ZB? ZB is, yeah, write down. Whatever you can. What is Z collector? What is Z collector? That's little difficult. Any answer? Z collector? How many are saying that it's 1 by Gm? When you are applying or when you want to find out the impedance at collector, you have to make base and emitter to 0. So there is no R pi. So as Ashish is saying, VB is equal to 0. So the current flowing through this network is 0. Current flowing through this network is 0 means the impedance is infinite. Right? So the ZC is infinite in this case. Now can you find out ZE? ZE. So I will not give the answer for ZE. You just write down whatever you think. If you need to know the procedure, I can help you in procedure. Okay, so procedure is as follows. If any network is given to you, and if there are multiple flow ports, these are the inputs. Let's assume that you have only 3: base, collector, and emitter. You want to find out ZB, then apply the known Thevenin voltage by keeping other terminals as ground and measure the current. VTH by ITH is going to give you the impedance. So here it will be R pi, right? So if you are keeping this ground, if you are keeping this ground, there is only one path, right? So similarly, you can find out for others also. So please write down the answer for ZB, ZE, and ZC.